4 degrees, 2 masters, 1 mission, pure logic. Hi everyone, I'm Cathy Liu, with master's degrees in statistics and finance, and a dual background in mathematics and economics. I've spent my life deconstructing complex systems. Today I'm not just teaching you how to find an answer. I'm teaching you how to master the logic of the quote-unquote unsolvable. If you've ever felt stuck on SAT geometry that ends in the next 10 minutes, let's dive into the problem. Let's take a look at our mission. In the figure shown, points A, B, C, and E lie on the circle. We are told that segment AC is perpendicular to segment B at point D, and we have a specific measurement. BD equals the square root of 346. Additionally, the diameter of this circle is 175. Now there is a very important constraint. AB is less than BC. It might seem like a small detail now, but it will be our North Star later in the problem. Our ultimate goal? To find the value of the ratio R equals CD over AD. Are you ready to start the investigation? Let's go. The question is, what do we know about AC? Any guess? Maybe some student will say AC equals 175, but why? From the question we only know the diameter equals 175, but it didn't tell us AC is the diameter. Here is a hint, look at the figure. The figure explicitly marks angle ABC with a right angle symbol. Based on the converse of Thales' theorem, if an inscribed angle is 90 degrees, the coordinate subtends must be the diameter. So, since angle ABC equals 90 degrees, segment AC is indeed the diameter. Therefore AC equals 175. Now we know AC equals 175, what else? Can we find any relationship between the sides? Let's review the geometric mean theorem, which has two parts. The first part is the leg rule. The square of a leg equals the product of its projection on the hypotenuse and the entire hypotenuse. Let's see the projection part. Imagine we have a light from point B toward E. The shadow for segment AB on AC will be AD. If we have another light from B toward C, the shadow for AB on AC will be AC itself. So AB squared equals AD times AC. Similarly, for BC, if the light is from B toward E, the shadow is CD. If the light is from B toward A, the shadow is AC, so BC squared equals CD times AC. The second part is the altitude rule. The square of the altitude to the hypotenuse equals the product of the two segments it creates on the hypotenuse. How can we find the shadow for BD? One light from B toward A, the shadow on AC is AD. Another light from B toward C, the shadow on AC is CD. So BD squared equals AD times CD. How can we prove it? We can use triple similarity. First, let's see triangle AD and triangle ABC. Angle BAD equals angle BC, and angle ADB equals angle ABC, both being 90 degrees. Based on the angle-angle criterion, triangle ADB is similar to triangle ABC. So AB over AD equals AC over AB, which means AB squared equals AD times AC. Second, for triangle BDC and triangle ABC, angle BC equals angle BCA, and angle BDC equals angle ABC, being 90 degrees. Based on angle-angle, triangle BDC is similar to triangle ABC, so BC over CD equals AC over BC, which means BC squared equals CD times AC. Third, let's see the angle relationships. Angle BAC plus angle BCA equals 90 degrees. Angle BAD plus angle ABD equals 90 degrees. And angle DBA plus angle DBC equals 90 degrees. From these we get angle BC equals angle ABD and angle DBC equals angle DAB. So triangle BDC is similar to triangle ADB based on angle-angle. This gives us BD over CD equals AD over BD, and we prove that BD squared equals AD times CD. Let's review congruence versus similarity. Congruence means identical in shape and size, and the scale factor k equals 1. Similarity means identical in shape but different in size, where k does not equal 1. Note that congruence is a specific case of similarity where k equals 1. How do we prove them? For side, all three sides are equal for congruence but proportional for similarity. For side, angle side, two sides and the included angle are equal for congruence. Two sides are proportional and the included angle is equal for similarity. For angle-based proofs, for congruence we need two angles and one side equal. For similarity we only need angle-angle, meaning two angles are equal. For right triangles, for congruence we use hypotenuse leg. For similarity, we just need a constant ratio of any two sides. Key properties: corresponding angles are always equal. Corresponding sides are equal in congruence but proportional in similarity. The area ratio is the square of the scale factor. Now, how to use the fact that AB is less than BC? Why do we have this in our question? This is a really critical application. Based on the leg rule, the ratio of a B squared over BC squared equals the ratio of a D times AC over CD times AC, which simplifies to a D over CD. Given that AB is less than BC, then AB squared must be less than BC squared, so we know AD is less than CD. We need to use this vital information later. Alright class, after our geometric journey, what ingredients do we actually have on the table? Let's take a look. First, through our leg rule and the constraint, we are absolutely certain that AD is less than CD. Second, by identifying the diameter, we know the sum of these two segments, AD plus CD, is exactly 175. Third, the altitude rule tells us that the square of the height BD equals the product of these two projections. Since BD is the square root of 346, their product AD times CD is exactly 346. Now our geometry has stripped off its mask to reveal an algebraic core. Our ultimate mission is to find two numbers whose sum is 175 and product is 346, where the first is smaller than the second. To make the math more fluid, let's translate our geometric language into algebraic symbols. We define AD as x and CD as y. With this, we have a classic system of equations. X plus y equals 175 and x times y equals 346, with the constraint x is less than y. This is the beauty of mathematical thinking. We have successfully downshifted a complex circle geometry problem into a pure algebraic modeling task. This ability to translate across disciplines is the key to standing out in the SAT and beyond. For this system, I first want to introduce method 1, quadratic modeling. Many students ask, why does a variable t suddenly appear here? Where does this equation come from? There are two ways to understand this. The first is the inverse application of Vieta's formulas. We know a quadratic equation with roots x and y expands into t squared, minus the sum times t, plus the product equals 0. Since we already have the sum and the product, we can reconstruct the quadratic equation directly. T squared minus 175t plus 346 equals 0. Here x and y naturally become the two roots of this equation. The second is the intuitive substitution method. If t feels too abstract, we can let y equal 346 divided by x. Plugging this into the sum equation gives us x plus 346 divided by x equals 175. If we multiply both sides by x, you'll find it turns right back into x squared minus 175x plus 346 equals 0. Using the quadratic formula, we calculate two results, 173 and 2. Based on our logical chain, the smaller x must be 2, which is a d, and the larger y must be 173, which is CD. If you want to avoid a messy quadratic method too, the algebraic identity method is your best friend. The biggest benefit here is dimension reduction. We stop dealing with second powers and instead use the elegant relationship between the square of the difference and the square of the sum. Look at this identity, the square of y minus x equals the square of y plus x minus 4 times xy. We plug in our sum and product, 175 squared minus 4 times 346, which equals 29,241. Taking the square root, we directly find the difference between the two segments, y minus x equals 171. Now we have the simplest linear system, a sum of 175 and a difference of 171. Adding the equations gives us the large number y equals 173 and subtracting them gives the small number x equals 2. This method bypasses the tedious calculations of the quadratic formula entirely. Finally, I want to show you the Cathy.L secret weapon. Prime factorization analysis. This is the number sense approach we highly recommend for time tests. Since we are looking for two numbers that multiply to 346 and add to 175, let's perform short division on 346. Dividing by the smallest prime 2, we get 173. We immediately discover that 173 is a prime number itself. This means the factor combinations for 346 are extremely limited. Only 1 times 346 or 2 times 173. Let's quick check the sums. 1 plus 346 is 347, which is no, but 2 plus 173 is 175, a perfect match. In just 2 seconds, we've locked in AD equals 2 and CD equals 173. In a race against the clock, this method is a lifesaver. The final solution for the ratio R equals CD over AD is 173 over 2, which equals 86.5. Before we finish, I have summarized the 5-step breakthrough for this problem. This is your master manual for success. First, identify, never ignore small symbols in a circle. The right angle marker is your only lighthouse for identifying the diameter and applying Thales' theorem. Second, connect. Similarity is the bridge between the angles you see and the lengths you need. The geometric mean theorem is the core of these integrated problems. Third, constrain. Conditions like a B is less than B, C are never just decorative. They are the filters that eliminate false answers during your final selection. Fourth, model. Master the transition from geometry to algebra. Strip away the shapes to reveal the simple sum and product equations. And fifth, solve. Don't just compute. Analyze. Pick the weapon, whether it's quadratic modeling, identities, or factorization, that fits the numbers best. Now that we have mastered the logic together, it is time for your final exam. I have prepared a logic challenge for you. The geometric structure is exactly the same, but our numbers have changed. This time segment BD equals 28 and the diameter of the circle is 106. Do not forget our North Star. Segment AB must be less than segment BC. Your mission is to find the value of the ratio R equals CD over AD. Comment your final answer below. I will be personally checking the comments to see who can crack this Cathy-style challenge first. Do not just calculate, analyze. That concludes our demo for today. I am Cathy Liu. We don't just find the right answer. We explore the undeniable beauty behind the logic. I hope you can take this rigorous logic with you to your next challenge. Thank you all.